When we talk about polynomials and roots and complex numbers, we should perhaps mention one important mathematical theorem, namely the fundamental theorem of algebra. And this theorem says that the equation polynomial equal to 0, when the polynomial is a non-constant n-order polynomial, then such an equation has exactly n roots. The coefficient in the polynomial may be complex or real or integer numbers, and the roots may be complex or real. And every root is counted with its multiplicity. So if we have a double root, that adds 2 more roots. If we have a root with multiplicity 3, we count this as 3 equal roots. Perhaps one small remark: what does it mean, non-constant? What's the opposite? What's a constant polynomial? A constant polynomial is a zero-order polynomial that may be either non-constant value, then it has no roots. This still would fit in this theorem, because order 0, number of roots 0, that would fit. But we can also have constant polynomial equal to 0, and this equation has infinitely many roots, and that doesn't fit in this anymore. So if we put the condition that a polynomial should be non-constant, then everything is fine. And what is important for us, if the polynomial is real, that means the coefficients are real numbers, then the roots may be complex, but then they come in pairs, 2 complex conjugate numbers. Let me illustrate this with a quadratic equation. Consider the equation 2x squared plus 3x plus 3 is equal to 0. When we compute the discriminant, we have b squared minus 4ac, which is 24, and 9 minus 24 is minus 15. So the first root will be minus b plus square root of minus 15 divided by 2a. But square root of minus 15 is no real number, it's a complex number. And if we write it as minus 3 plus square root of minus 1 times 15, then square root of minus 1 is I, the imaginary unit, and we can write it as minus 3 plus square root of 15 I divided by 4. And the other root, x2, is minus 3 minus square root of minus 15 divided by 4, and with the same manipulation we get minus 3 minus square root of 15I divided by 4. So these two numbers differ in the size of the coefficient at I, and these numbers are called complex conjugate, something like here and here. So this illustrates that a real quadratic polynomial, if it has complex roots, then they are complex conjugate. And fortunately, this is true even for higher order polynomials. Higher order polynomials may have a bunch of roots, some of them being real, some of them being complex, but the complex roots always come in pairs of 2 complex conjugate numbers. And this is a convenient result.